All right, lesson 3.4. I do say the same thing every time. Wrapping up our unit on probability. Woo. Okay. So we're kind of just doing some practice problems with permutations and combinations. Refresher, permutation, order matters. Combination, order does not matter. And you don't need to memorize the formulas. You just need to know how to use those buttons in your calculator. So we started kind of looking at ones where there was more than one like possible way of satisfying these outcomes. So this one's kind of similar. So an event planner is deciding what food to include in a buffet. The caterer has offered 6 cold dishes and 7 hot dishes. Of the 13 dishes that are offered, the event planner will choose 5. A says, in how many ways can the event planner choose 5 total dishes if the number of hot dishes must be greater than or equal to 4? All right, so there's kind of 2 ways we could satisfy this condition. We could have 4 hot dishes, and if we have to total 5, that means 1 would be cold. Or we could have all 5 be hot dishes and no cold dishes. Okay, so we're basically going to create a combination for each case. And combination because the order that we select these doesn't matter. They're going to be the same hot dishes. So let's see, we have 7 hot dishes offered, and we get to choose 4. And so I'd multiply that to the number of ways I could choose 1 cold dish. So I have 6 cold dishes, and I'm going to choose 1. Okay, so there's that first one. Or, so I'm going to add this to, or I could have 7 hot dishes and I choose 5, and 6 of the cold dishes we choose 0. This number right here, I got 210. This number right here, I got 21. Adding those together, 231. Okay. Part B, we could do a couple ways. Let's read through it here. It says, in how many ways can the event planner choose 5 dishes if the number of hot dishes must be less than 4? So we could go through and do 0 hot, 5 cold, 1 hot, 4 cold, da 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 da. But another way we could do this is kind of almost like the complement thinking. If we can figure out the total number of ways that we can just choose 5 dishes out of all 13 of these, and then just subtract off basically everything except these, that'd be the same number as all the possible options that must be less than 4. But you could go through, if this makes more sense to you to do it how we've been doing it, you could do 0 hot, 1 cold, 5 cold, 1 hot, 4 cold, 2 hot, 3 cold, 3 hot, and 2 cold. You could go through and calculate the exact same way we just did. If you want to do that, you can. See if you get the same answer. Another way is we can find our total number of ways. And this is pretty easy to do with one combination. We have 13 total dishes and we need to choose 5. So that number is 1,287. And then we just subtract off what we found in part A, which was everything except what part B is asking for, if that makes sense. So then I got that final answer of 1,056. So some of those problems might be set up that way, where like in part A, they ask you to calculate the number of ways, and then part B is like everything except part A, and you could probably get to your answer quicker doing it that way, like just find your total minus the number of ways that we already calculated. Or again, you could set up 4 different sets of combinations as well and just add them together. This or this or this or this. And get that answer that same way. Okay, let's try some with cards. Okay, so the table is just again showing you the standard deck of cards, the suits and spades. Oh yeah, those are the suits. I'm like, why am I trying to say suits? Suits and then just like all the number values in the face cards. How many 5-card hands contain exactly 3 diamonds? So a 5-card hand is like you just get dealt 5 cards. It's a set of any 5 different cards. Okay, contain exactly 3 diamonds. I'm just going to draw myself a little picture. That means there's only one option. It means of my hand of 5 cards, 3 of these are diamonds. Sorry, those diamonds are not my best drawing. There you go. Meaning these, we don't know specifically like what suit or anything. We don't care. They just cannot be diamonds. Where? I struggle so hard to find diamonds. Okay. So basically, we'll come up with a combination for these 3 cards. And we'll come up with a combination for these other 2. Does the order matter in which I draw these cards? So for example, if I got a 2, 3, 4, is that different than a 4, 3, 2? No. So again, combinations. How many total diamonds are there that we're choosing from? 13. Yeah, there's 13 of each suit. So this right here would be 13 diamonds, and we're choosing 3. So how many cards are not diamonds? 52 minus 13. What'd you say? 39. So these 39, we're going to choose 2. And we'll times these together for my different combinations of each in my 1-card hand. Okay, so for the diamond number, I got there's 286 different ways you could choose 13 different diamonds. Times, and then the other suit, obviously there can be more, 741. Seems like there'd be more than that. $211,926 different ways. Crazy. Okay, the only last thing we need to do is we're going to do like probability with these permutations and combinations. And so basically we already know how to count the number of ways. So you just do your total numbers of success ways over the total number of possible ways. Is how we calculate probability. Just the way we count it, we're going to use permutations and combinations. Okay, so we're just going to do 2 examples of this. There are 8 acts in a talent show. An acrobat, a comedian, a juggler, a magician, a pianist, a singer, a violinist, and a whistler. A talent show host randomly selects and schedules the 8 acts. Compute the probability of each of the following acts. So event A says the singer is first, the acrobat is second, the comedian is third, the pianist is fourth. Event B, the first 4 acts are just those 4 in any order. Ooh, keyword there, in any order. That's a dead giveaway. That order doesn't matter. Combination. Here, it's assigning my acts in a specific order. Singer's first, acrobat second. That would be different than doing the acrobat first, singer second. So that one would be permutation. Order matters. All right. So before I calculate the probability of each event, that's what this notation means, let's just practice counting the number of ways. So I'll start with event A. Number of ways A can happen. So there's 8 total acts, and I'm picking how many? 4. 8 pick 4, where the order matters, meaning singer, acrobat, comedian, piano player is considered different than piano, acrobat, singer, comedian. All right, that I get 1,680. For event B, the only thing that changes here is the order does not matter. So I'm going to do 8, choose 4 with a combination, and there's only 70 different ways. So the number of ways that this specifically happens, that the singer's first, acrobat second, comedian's third, piano player's fourth, there's only one way that could happen. So if I'm calculating my probability, it's that one specific outcome out of 1,680 different ways. Write your answer in the fraction. Perfect. We can leave it like that. Event B, the first 4 acts are that group. And remember, with combinations, we count this as one outcome. And if I were to switch around the order, that's still considered the same outcome. So there's only one way I can group these 4 in any order out of a total of 70. So basically, the only thing that's kind of like different with these is you're just using permutations and combinations to calculate the total number of ways. Oh no. No. Okay. Last one. Pretty similar. Okay, this time we have 8 streets, and they're named after 8 tree types: ash, birch, elm, fir, maple, oak, pine, willow. A city planner randomly selects the street names from the list of 8 tree types. Compute the probability of each of the following. A, that the first one selected is maple, followed by birch, and then willow, in that specific order, permutation. The first 3 streets are maple, willow, and ash without regard to order, combination. So I kind of just like to first, let's just calculate the number of ways A can happen. 8 pick 3, where the order matters. 336 different ways we could do that. Number of ways B can happen. 8, choose 3. 56. Everybody remember how to use the permutation combination buttons in the calculator? Okay, good. For some reason I have to show my geometry paper 8 times, so I push into tangent and science. It's cute. All right, so probability that A would happen would be 1 out of 336. B, 1 out of 56. Now, it's not like in real life, it's not always going to be 1 over that. Like sometimes you might use permutations or combinations to count how many like successful ways. But in ALEKS, I think these are the only types of probability problems I threw in there with permutations and combinations. All right, wow, how fun. Now, previous like problems you've done where you didn't know permutations and combinations, you can use them to count your number of ways. Like the fundamental counting principle ones, like it's easier for you to use permutations or combinations, you can. You just gotta decide if order matters. Wow. I thought that would maybe take a little while.